Hello, I'm Robert Campbell, and welcome to Book for Japan, where we meet the most innovative men and women from all walks of life here in Japan. Each of our guests chooses one book that inspires him or her, and we'll be looking into that for clues about how he or she looks at life and the world. Today, I'll be talking with Hitoshi Murayama, the brilliant young physicist, a world leader in the field of particle theory, and, according to many, the man closest to solving the puzzle of the universe. Murayamaさんですね。
はい。
キャンベルです。
はい、どうも。ようこそ。
いや、一度やっぱり訪ねてみたかったので、今日はとても嬉しい。
今日来ていただいて嬉しいです。
よろしくお願いします。
はい、よろしくお願いします。
Hitoshi Murayama, theoretical physicist.
As you watch the ball going up, it kept slowing down up to some point, but then it started picking up speed and sped away. This colloquium today is, as you see this.
Since 2000, he has been a professor at the University of California, Berkeley. In 2007, at the age of 43, he was also appointed director of the Kavli Institute for the Physics and Mathematics of the Universe, a newly founded international research center at the University of Tokyo. In addition to research on the origins of the universe, Murayama is enthusiastically involved in outreach activities, giving public lectures and talks for children. He spent his adolescence in Germany and has since shuttled between Japan and other countries. Murayama has devoted his life to probing the limitless wonders of the universe. What has he glimpsed behind it all?
今日私は初めてここに来て驚いたのがですね、黒板が非常に多いですね。
もう黒板だらけです。
私はまあ今頃の科学者といいますか、やっぱ科学っていうのは全てパソコン、それをやっぱり黙々とモニターに向かって仕事をしてコミュニケーションをするのかなと思ったら黒板なんですね。
やっぱりその黒板っていうのはなんていうのかな、まず議論するときにそのアイデアが割と素直に出せる。で話をしてる時っていうのはいつもほとんどブレインストーミングしてるような感じなんですよね。で研究って何がうまくいくかわからないじゃないですか。どの分野もそうだと思うんですけども、で今こんなこと困ってて考えてるんだって、でそういう話を始める時に、いや実はこれがあって書き始める時に、コンピューターで例えば式を書いて示そうと思っても結構大変ですよね。
時間があって変換をしたり、
そうなんですね。だから自分でじっくり考えて文章にまとめ上げる時には別にそれでも構わないんですけど、すぐと人に話したいっていうそのスポンテイニアスな感じの時っていうのは黒板が一番早いんですよね。
ホワイトボードではダメなんですか？
それは好き嫌いなんですけども、ホワイトボードってペンを使いますよね。でホワイトボードのペンっていうのはしばらく例えばキャップ開けっぱなしにしておくと乾いちゃって使えなくなるじゃないですか。
かすれたり。
でずーっと書いててもだんだんかすれてきて使えなくなってイライラするんですね。
それだけですか？
いや、それが一番大きい。
そうですか。きっと感触というか筆触というか、
それもありますね。
音とかですね。やっぱり強弱、ホワイトボードだと強弱あまり出ないじゃないですか。
そうですね。
黒板だと最後に白木で点を打つとかですね。カッカッカッカッカッカッと書いたり。村山さんは1年の半分以上を日本とアメリカを往復しながら仕事をしていらっしゃるんですね。
アメリカではバークレーの大学でポジションがあって、 で、で家族も向こうにいます。で授業もしないといけない。でこちらではこのカブリ IPMU の機構長の仕事があって、でそれはまあ授業とかはないですけども実際にその運営をする仕事があるわけですね。ですからどちらにもある程度いなければいけないので、まあどうしても行ったり来たりしなきゃいけない。
そうですね。それはどちらが過ごしやすいですか？
それは微妙ですね。もちろんアメリカでは家族もいますから、そういうそのアットホームな自分の家でもあるし、まあそういう落ち着いた気持ちになれるわけですけれども、で日本では、そうですね、やっぱり食べ物とかは日本美味しいじゃないですか。でそういうのはやっぱホッとするところもあるし、一つお風呂ですね。そのアパートのまあちっちゃいアパートですけれども、お風呂は普通の日本のお風呂なのでこのぐらいちゃんと深さがあって、こうやってこう座って中に入れるじゃないですか。でアメリカだと普通のアメリカの家ですからもっと浅くてこう寝て入るんですよね。やっぱり座った方が気持ちいいですね。そういう時は日本人かな。
お風呂に。
Murayama is the director of the Kavli IPMU, whose mission is to be a top-class international research center. Researchers here in the fields of mathematics, physics and astronomy pursue a wide range of interdisciplinary studies on fundamental questions regarding the universe. Kavli IPMU has around 100 scientific staff, including 18 senior researchers who are world leaders in their fields. 60% of the staff are from outside Japan, reflecting Murayama's desire to create a truly international and interdisciplinary institution.
What were the founding principles of Kavli IPMU? What is its mission in terms of research?
Our mission is actually quite simple. As a child, I think everyone at one stage looked up at the sky and thought how beautiful the universe was. All sorts of questions must have come to mind. How did the universe begin? What lies in the future? Why am I here? The minds of small children and adults alike are filled with these almost philosophical questions. Our mission is to find the answer to these fundamental questions. To do so, it was clear that a conventional university institution wouldn't work. For example, the University of Tokyo's mathematics faculty is in one part of Tokyo, and the physics and astronomy faculties are in a different area. So there's very little opportunity for interaction. Ideally, people from different fields should be able to work together to tackle a common goal. But there was nowhere to conduct that kind of research across disciplines. Here we have mathematicians, physicists, and astronomers, but they all work together in a kind of melting pot environment. We hope it will lead to something new and exciting. That's the founding principle of this institute.
As director, what exactly is it that you do here?
All kinds of things. When the institute was founded, we had to start from scratch. This building didn't even exist, and we had no scientific staff. So it was really tough. It was especially tough because we wanted to create a truly international research institute. Around 60% of our researchers are from outside Japan. But when we started, we had to learn how to invite and accept people from outside Japan and help them find a home in Japan so that they could carry out research. There were all these details to worry about. It was really difficult. For example, suppose someone from outside Japan were to apply for a credit card in Japan. His or her application would probably be turned down. Same with a cell phone. If the person's staying at a hotel and has no permanent address, he or she wouldn't even be able to apply. So we had to provide support for setting up base in Japan. We once asked Henry Tai, a researcher from Cornell University, to give a lecture. He was instrumental in coming up with inflation theory, which has become a key idea in cosmology. When he arrived at the institute, he looked at me and said, "You saved my life." I asked him what he was talking about, and he explained that on arriving at his hotel, he thought he'd better change some dollars into yen. So he went to a bank and tried to draw out money from a cash dispenser using his American ATM card, but it didn't work. After visiting 7 banks in vain, he was in a state of panic. He returned to his hotel in despair because, without cash, he couldn't even get to the Institute. Out of sheer desperation, he accessed the Kavli IPMU website and found information that I'd posted on where to go to draw out cash. If you go to a certain type of convenience store or post office, they have ATMs that accept foreign bank cards. So he went to a convenience store and was able to draw out some money, which is why he said I'd saved his life.
Dark energy is causing this acceleration. It's ripping the universe apart. So I had to actually change that. And also like to give you a full...
As director of an emerging international research institute, Murayama is striving to create an ideal environment for his scientific staff. One of his innovations at Kavli IPMU is a daily tea time. At 3 p.m. a chime sounds and scholars gather in the atrium where they engage in wide-ranging discussions. Attending tea time is obligatory, unless someone has an appointment outside the institute.
So, why did you come up with the idea of having a tea time gathering?
Well, I had various things in mind, but basically, since we're all members of the same institute, I felt it was important to get to know each other. Also, in terms of promoting research across disciplines, it's very common for one person to know virtually nothing about someone else's field.
And it's embarrassing to ask.
Exactly. But in this relaxed atmosphere, it's easy to ask someone to explain something unfamiliar that seems interesting. People gradually learn about each other's fields. People in different fields seem to speak an entirely different language. So we have to begin by understanding each other's language. This setting allows us to interact and learn naturally, the way children do.
So if you can measure the HOD, right? If you know this slope, say n proportional to m to some power. Okay.
How are you, Robert Campbell?
I'm Simon.
Simon.
Yes, our youngest member.
Our youngest member of the faculty. Hi.
Well, the nice thing here is we have, well, Gaston is an astronomer. I'm a theoretical physicist working on sort of very mathematical things. Yeah. And we have actual mathematicians and we have string theorists, particle theorists. So these tea times are great for just interacting with each other. And I don't know how many actual papers were written in this way, but it's very good to sort of stay up to date with what's happening in other fields and just being better educated, and that's very nice.
Most of the times I talk with people that I collaborate with, but I also take from time to time the opportunity to talk with other people about a variety of topics, and I think that makes everyday work more substantial, or makes you it gives you the opportunity to open your mind a little more.
In the center of the atrium stands a pillar bearing the words of Galileo. The laws of the universe are written in the language of mathematics. This is the founding philosophy of the Kavli IPMU. All the formulas scrawled on blackboards open a window on the nature of the cosmos. From time immemorial, scholars have been mesmerized by the mysteries of the universe. 400 years have passed since Galileo began looking at the stars through a telescope. Our first journey into space was 50 years ago. Just how far have we come in unlocking the mysteries of the universe?
Space research has made tremendous progress over the last decade or so. What stage have we reached, in fact?
Well, take telescopes, for instance. We're now able to build enormous telescopes that are highly efficient. They allow us to see what we couldn't see before and observe things that are far, far away. This is a photo of what used to be the furthest visible galaxy.
Oh, taken by the Hubble telescope?
Yes, you can see all the galaxies in the distance. But if you enlarge this, you can see what look like red spots. This is a galaxy that is 13.2 billion light years away. In other words, it's taken that long for light to travel from there to the Earth.
So we're looking at light from 13.2 billion years ago.
Yes. Likewise, the sun we see in the sky is what the sun looked like 8 minutes ago. The Andromeda, 2.5 million years ago. So if there were people out there at this very moment, what they'd be seeing is Earth when there were monkeys, but no humans.
I see.
Our solar system is in the center of the Milky Way. We now know that there is a black hole with 4 million times the mass of the sun in the center of the Milky Way.
A black hole?
Yes, right here. This is the Milky Way. It looks like a river. This area here looks dark because it's shrouded by dust, but it's not really dark. Using infrared rays, it's possible to see beyond the dust. So we can now observe the movement of stars in the galactic center. It takes a lot of time and patience because the observation has to be conducted over a span of several decades. Researchers spend decades following the movement of each star. If you watch closely, you can see how this star turns sharply.
I see what you mean.
So something with enormous mass must be exerting a pull on it.
It's under the influence of gravity.
Yes, and studies have shown that it's been pulled by something with 4 million times the mass of the sun. It couldn't be a star.
And so it's
a black hole.
Ah, I see.
It's called a black hole because whatever enters it can never escape. And you can observe things being sucked into the black hole in the galactic center. If you watch carefully, you'll see a flare of light. Here it comes. See how it lights up?
Oh, yes.
It becomes dark again, but it continues to be bright for about 30 minutes. This is actually a ball of gas that's close to the black hole. It's about to be engulfed by the gravitational pull of the black hole. Once it's drawn into the black hole, it can never escape, and no light will make it visible. But right before it's engulfed, it flares up, as if it were crying out at the hour of death. We see its final light.
What sort of projects or themes are you working on now?
Major discoveries were made in 1998 and 2003. We learned that we know hardly anything about what 96% of the universe is made up of. At school, they teach you in science that all matter is made up of atoms. Our bodies, this table and computer, everything is composed of atoms. But actually, atoms account for very little of the matter in the universe. Most of the universe is made up of what's known as dark matter, which we know very little about. What's even more exciting is the discovery that the rate at which the universe is expanding is accelerating. That doesn't sound right, does it? Gravitation attracts.
It draws things together.
The universe began to expand following the Big Bang, but it's constantly exposed to gravity, so the rate of expansion should be slowing down. But it's accelerating, so something must be pushing it outwards.
You mean from the inside?
Yes. We don't know exactly what it is, but it's making the universe expand faster and faster with more and more energy. So it has to have some kind of energy itself. This has been named dark energy. And like dark matter, we know very little about it. But we know that both have played a very important role in the history of the universe and will continue to do so in the future. This is a computer simulation of what the universe would look like 13.7 billion years from now if there were no dark matter. Very flat and smooth.
There's hardly anything there. Everything has been scattered away.
There are no clusters.
It just stretches out.
But with dark matter, there exists a gravitational force that draws dark matter together. Once a cluster is formed, it begins to draw atoms towards it. eventually leading to the birth of stars and galaxies. So you could say that dark matter gave birth to the universe. But since we don't know what it is, it's like trying to find one's mother from whom one was separated at birth. You might want to know who your mother was.
You were separated, but she exists.
Yes, she's somewhere around and was responsible for creating the structure of the universe, creating galaxies and stars. We want to find out more about her, so finding out about dark matter is one of my key research themes.
We have a discovery. We have discovered a new particle, a boson, most probably a Higgs boson.
In July 2012, the discovery of an elementary particle that could be the Higgs boson was hailed around the world as the breakthrough of the century. The Higgs boson is a key to understanding the mass, or weight, of matter in the universe, as it would help to explain how the universe was formed. It has been nicknamed the God particle.
It's clear that the Higgs boson played an essential role in the formation of the universe. The Higgs boson is a particle that exists throughout the universe. In fact, the universe is packed with them. If they were to suddenly disappear, your body would disintegrate in 1/1000th of a second.
I become tiny bits and pieces.
Yes. The Higgs boson is what provides mass to matter. It creates order. It plays a fundamental role.
Kind of glue?
If you like. Previously, it was believed that there were only two kinds of particles. Particles that formed matter, and particles that transmitted energy. Light, for example. Those are photons. The Higgs boson is an entirely different type of particle that is able to create order. To be more specific, I'm going to use a very simple analogy, like something in a manga. When the universe was born, it resembled the vapor coming from a volcanic eruption. Vapor is composed of water molecules moving about randomly. Like vapor, the universe initially had no order. But when water cools, it becomes ice. Ice molecules form rows that are nice and neat. It's very orderly. The Higgs boson is what brought that kind of order to what was initially a chaotic universe. By this, I mean that when the universe was hot, it was like a kindergarten, between classes, like this.
Each child is moving in a different direction, playing as he or she pleases.
You'll probably remember that kindergarten kids just do as they like.
You're right.
They think only of themselves. No matter how many times the teacher tells them to come inside right away, they won't follow orders. But then comes the Higgs boson, waving a magic wand. And presto, the kids immediately become obedient and sit at their desks.
Right there in the classroom.
The Higgs boson enables all known elementary particles to have order and mass.
Ah, so that's what it does.
I said that if the Higgs boson were to disappear, your body would disintegrate. What I mean is that your body is made up of atoms surrounded by electrons. If the Higgs boson disappeared, the electrons would lose all mass and start to zoom around at the speed of light, causing your body to disintegrate.
Suppose we eventually find out what the Higgs boson is all about, or what actually constitutes dark matter. How will this contribute to enhancing the way we live on this planet?
To be honest, I don't think it'll actually help in any way. It's a very good question, though. A fundamental one at that. How did the universe begin? Why do we exist? How are our bodies formed? How did we come to live on this planet? Finding answers to such questions won't help us obtain more food or help in any way.
We won't become ageless.
No, but human beings are creatures that seek such knowledge. From an early age, we're full of curiosity. What are we? Where did we come from? What will happen to us in the future? We exist because of this planet, which is made up of the debris from a star explosion that took place way back in time. Where did that star come from? If it was made up of atoms, how were these atoms formed? It could never have happened without the Higgs boson. Trace the evolution of the universe, and you see that some matter has existed since the beginning. Zooming in on that will provide us with an answer to where we came from. So it means a lot in terms of considering what we are. I believe it'll help us find answers to fundamental questions regarding our existence.
Murayama says he's been inspired by a book written by Shinichiro Tomonaga, Physics Through the Looking Glass, and especially a chapter titled Photon's Trial. Tomonaga was awarded the 1965 Nobel Prize in Physics for developing the super many-time theory and renormalization theory. He also wrote various books in straightforward language to help people to understand physics. Later in life, he gave talks to children to promote understanding and interest in natural science. These efforts made a strong impression on Murayama.
被告の答えは甚だ奇想天外なものでありました。私は2つの窓の両方を一緒に通って室内に入ったのです。私はこの答えにあっけに取られました。一体一人の被告が2つの窓の両方を一緒に通るなどということが可能でしょうか。状況判断はあくまであらゆる状況を注意深く観察して初めて下さるべきであって、狭いあるいは不精密な経験によって得られた規制の概念によって無反省に下された独断であってはならない。
In this story, photon, one of the elementary particles that constitute matter, is standing trial. The prosecutor doesn't believe a puzzling statement she makes about entering a room from two windows at the same time. So her attorney conducts an experiment to prove that she is telling the truth. The story explains in simple terms the basics of quantum mechanics and the joy of discovering nature's secrets.
I found Photon's trial very exciting, full of suspense. It made everything very clear to me.
Well, I'm glad to hear that.
It was really interesting. How old were you when you read this?
Well, I don't remember exactly, but I think it was after I entered university.
And how did the book influence you?
A photon is a tiny light particle that we presume is always in one specific location at a time. But the book explains, in the form of a trial, that when there are two windows, it can pass through both windows at the same time. It's an interesting way to frame the information. Normally, it would take years of studying in order to understand what this is all about. Tomonaga was a physicist who won the Nobel Prize. In a sense, he was the one who completed the theories regarding electrical and magnetic forces. But he wrote this relatively informal book to convey the astonishment he felt during the course of his research. What's more, he explains the process through which he arrived at his really amazing conclusions. You can tell that he put a lot of thought into how to explain things in layman's terms.
His desire to communicate certainly comes across quite clearly.
Yes, it was a revelation to me, and it inspired in me a desire to be able to convey to people what I'm doing in my research. I was also inspired by the way Photon's trial was written. It emphasizes the importance of the research process. Our research is fueled by a desire to find answers to the unknown, but reading this made me realize how important the process is. Through the exchange that takes place between the prosecution, the defendant Photon, her lawyer, and the judge, your premises and assumptions are gradually proved wrong, and you start to see things in a different way. That process is made explicit, and it made me realize that this is what research is all about. I reread the book after becoming a scientist. It made me reflect on the fact that we are often bogged down by preconceptions, and that it's really important to be able to see things without bias. That, I think, is the underlying message in the passage I read out, and it still strikes a chord with me today.
Murayama was born in Tokyo in 1964. He was a sickly child and had to have intravenous medication several times a month. As a result, he was often unable to go to school.
What got you interested in the universe in the first place?
I'm not really sure. It wasn't as if I grew up reading books about astronomy as a child. Actually, I wasn't a very strong child. I'd quite often have to stay home from school, and I'd watch educational programs on TV. There was one really interesting program about a grilled eel vendor. There he is fanning the delicious eels, and this strange man keeps coming to sniff the delicious aroma of the grilled eels. Oh, that smells good. The man comes every day just to breathe in the appetizing aroma of the eels. Eventually, he starts to get on the vendor's nerves. And one day, the vendor says, "You've been coming every day to enjoy the aroma of my eels, so you need to pay your bill." And the bill is tens of thousands of yen. The question is, does the vendor have the right to demand payment?
That's a tricky question.
You think so?
Yes.
So the program then starts to look into what constitutes aroma. The vendor grills the eel, and as the meat cooks, it releases tiny particles into the air, which then enter the man's nostrils to be perceived as a scent.
So he's absorbing the essence of the eel.
So he has to pay the bill?
Well, I guess so. But he can't prevent the particles from entering his nose.
But he takes the initiative to come and enjoy the aroma.
And in doing so, he's exerting his will.
Right. Anyway, it was that sort of program, cleverly designed to trigger a strong interest in what it means to be able to smell something. And it left a very strong impression on me. It made me think that physics might be a lot of fun.
When he was 11, Hitoshi moved to West Germany because of his father's work. He returned to Japan 4 years later. But having lived abroad at an impressionable age, he found certain Japanese values jarring. He writes about how he felt at the time. In Japan, I'd be going to junior high school. That's when younger students start to defer to older students. But I was in Germany instead. Friends from Japan told me about this age-based pecking order. I just laughed. Why be deferential with a fellow student? I could never understand that sort of Japanese mentality. In 1982, Murayama entered the University of Tokyo to major in physics. But the classes didn't interest him, and he spent most of his time with friends or playing in the university orchestra. He did go on to graduate school though, and after that he decided to pursue his studies outside Japan. He became a postdoctoral fellow at the Lawrence Berkeley National Laboratory in the United States. Then joined the faculty of the University of California, Berkeley as a professor. These days he is recognized as one of the world's leading physicists.
You were studying physics at university.
That's right.
And from there you specialized in space science. Did that go smoothly?
Well, it was a gradual process. I'd always been interested in fundamental questions regarding our existence. Questions like, what are we made of? To pursue the answers to such questions, I studied particle physics for a while. This is a field that concerns tiny elementary particles. Our bodies are made up of atoms, and inside each atom are electrons, which are elementary particles. The atomic nucleus includes quarks, which are also elementary particles. By understanding what these particles are and how they interact, it's possible to understand all aspects of our immediate surroundings. That's why I was attracted to the field.
So, how did your interest in the universe help your research on the theory of elementary particles? Where was the overlap?
I didn't realize what it was right away, but gradually I saw that when you trace the universe all the way back, you see that the whole expanse, stretching out to a distance of 13.7 billion light years, started off as a tiny speck that was smaller than a single atom. In other words, elementary particles were of tremendous importance at that time. So, in order to solve macro-sized problems, such as how the universe began and what its destiny is, an in-depth knowledge of elementary particles is essential. And an effective way to study elementary particles is to think of them in terms of the universe. This understanding came about gradually, and then suddenly it all clicked. My research on elementary particles in the universe all came together.
I'd like to turn the hands of the clock back to when you were in junior high school. You were in Germany at the time. Usually when someone spends their formative years outside Japan, it can be difficult to fit in with how things are done in Japan. What was your experience?
It was a bit of a struggle for me, especially as a university student. Senior high school was a problem too. In Germany, I never used polite language to a fellow student just because he or she was older than me.
Whereas in Japan, the difference in age, even if it's just 1 year, dictates the level of politeness to use when speaking to that person.
When you're meeting someone for the first time, you try and ascertain whether he or she is older or younger than you. You both feel awkward until you know what level of politeness to use. I've always seen that as a bit of a waste of time, actually.
Well, since my field of expertise is Japanese literature, I don't think of it as a waste of time. But it's certainly not very productive.
It's rather frustrating for someone who arrives in a new environment and wants to start researching right away. Of course, I appreciate the good aspects of Japanese culture, the fact that people are considerate of each other and try to conform so that everyone can get along together. But because you're expected to give consideration to other people's feelings, I sometimes find it difficult to be myself when I'm speaking in Japanese. The moment I switch to English, I can say what I want without constraint. So that's a big difference, I feel. I remember attending my very first international conference in the States. I was just an unknown postdoc, so I was thrilled to have been invited to give a presentation. And afterwards, scientists whose papers I'd read and thought highly of came up to me to say they'd enjoyed my talk and were looking forward to hearing more from me. I was elated. Next up was a leading scholar, and to my surprise, he was openly criticized. People said he ought to be ashamed of himself for giving such a feeble presentation. That made me think I'd come to the right place. I felt very encouraged and motivated. I realized then that, unlike in Japan, if you make an effort, you can be rewarded in the form of a raise or improved benefits. You can also draw the attention of a headhunter. So there are many incentives for achieving success.
That's true.
Whereas in Japan, you don't have that kind of system in universities. In fact, it's considered uncouth to talk about money or benefits.
No, it's never mentioned.
In the States, though, and this is actually a bad thing, people who are flashy are the ones who get on in life.
People who are pushy.
Yes, assertive people are able to achieve great success. There are both good and bad sides to this. But I think when you're young, it really is important to receive that kind of recognition, to receive that kind of encouragement.
13.7 billion years have passed since the Big Bang and the birth of the universe. How did the universe begin? And what lies ahead?
This is the limit.
Yeah.
Okay.
That's the limit. Yeah.
So, what is the ratio like?
In his quest to solve the mysteries of the cosmos, Murayama engages with researchers in various fields. What is his vision of the future?
Do you think it will be possible to narrow things down to one final mystery in our lifetime? Will we be able to solve that ultimate question about the universe?
No, that's hardly likely to happen. Of course, researchers believe that they'll be able to find an answer to a number of specific questions. For instance, the nature of dark matter may be revealed over the next decade. In fact, we'll probably be able to solve quite a few mysteries, but I don't think we'll find the answer to everything. One solution tends to lead to another puzzle. In that sense, I think it's going to be a never-ending challenge that we have to face.
You talked about how the Big Bang resulted in the birth of the universe some 13.7 billion years ago. That kind of time and scale is beyond imagination.
But human beings are pretty adaptable. You get used to it.
I have the feeling that your sense of time is different from that of other people.
Perhaps so, but not in terms of everyday life.
Is it possible to strike a balance?
People are very adaptable. Even when you find yourself in an unusual environment, you soon get used to it. You can get used to a bad smell, for example.
I guess you can.
You may start off feeling overwhelmed by a time and space scale that you hadn't considered before, but your brain gradually gets used to it. Even when dealing with tiny elementary particles, you learn how to visualize particles the size of 10 to the power of -13 or 16. It's like the way a child comes to understand the difference between a meter and a kilometer. For a child, a kilometer seems like a long distance. Walking that distance repeatedly over the course of several years will give the child an idea of how long it is compared to 1 meter.
Thinking about the universe inevitably makes me think about the future of the human race. It makes me reflect on life and death.
I don't necessarily try to draw parallels between the universe and human existence, but there's a very close connection between the two. For instance, climate change is a big topic these days. The temperature is expected to rise 1 degree Celsius over the next several decades. I think most people don't think of that as a major problem. But to me, taking into consideration that the Earth is 4.5 billion years old, it's shocking to think that the Earth's temperature may increase 1 degree in such a short time. On the other hand, there's always part of me that's aware of the fact that there will probably be no Earth 4.5 billion years into the future.
The mechanism of the universe and its secrets. What do you think is the ultimate significance of this for the human race?
Understanding ourselves. A lot of space phenomena are pretty stunning. Take a galaxy like the Milky Way. As the years go by, galaxies age and start to weaken. Most of the galaxies we see today are heading for death. But galaxies are drawn together by gravitation, resulting in frequent collisions. Merging provides them with energy. The collision creates a mixture of gases contained in the galaxies, which gives birth to new energy.
You mean they're reborn?
Yes, new stars are born. That's how the matter from which we're made was created. We are literally made of stardust. Our bodies are composed of dust particles produced when a star exploded. What are we? In a sense, we are stars.
And the stars are us.
You could say that, yes.
A lot of people say that basic science, theoretical science, knows no boundaries, that there's no sort of national or geographical, cultural sort of difference between people who are interested in studying the secrets of the universe. And I've always wondered about that there must be some sort of cultural or linguistic difference between people who come from different backgrounds. Talking to Professor Murayama today, I realized that there really isn't much of a big difference, that things don't really change, conditions don't really change from country to country. What's really important is the passion that the men and women who work here together at this center share in their pursuit for truth in astronomy, physics, and the mathematic sciences.
Hitoshi Murayama, theoretical physicist. A man who fuses the Japanese mind with a global perspective. The architecture of the universe is gradually being revealed, but beyond each puzzle solved lies another. Murayama expresses his philosophy this way. We share a common destiny with the universe. By studying the universe, we reflect on who we are. So we should advance our understanding of the universe. And in that way, we will advance our understanding of ourselves. Ever the youthful adventurer, Murayama continues to explore the limits of knowledge.